Okay, so I'll bet that most of you are familiar with this, but this is something that we kind of have to have a deep conversation with ourselves, because we can sometimes trick ourselves into not remembering correctly the influence of the melting and boiling point, or freezing point, right? Melting, freezing, same thing. Freezing and boiling point of compounds, the influence of the freezing and boiling point of compounds by solutes that are dissolved in them. Okay? Anybody live in a place where it snows, right, would know that to prevent the ice from accumulating on the roads, oftentimes they will sprinkle salt on the roads. So from that experience, you know that salt alters the freezing point of water. Salt alters the freezing point of water. Now, the difficult part becomes conceptualizing how it changes the melting point, or the freezing point, melting point of water. All right, how does it change the freezing point of water? Okay, it changes it, right? Meaning it's no longer going to freeze at 0 degrees Celsius. But sometimes people will say, oh yeah, it changes it, it shifts it, so it won't freeze at 0, it'll now freeze at 10 degrees Celsius. If you think about that and hold still and think, if it freezes at a higher temperature, 10, 20, 30, then adding salt to ice would not help it thaw, right? Because what we want is we want the ice to now thaw, we want it to melt to water. So, for example, if the temperature outside your house was minus 10 degrees Celsius, you would expect any water outside to be frozen, because water freezes at 0 degrees Celsius. So if you have ice on the ground, right? Here's some ice cubes on the ground. It's frozen at negative 10 degrees Celsius. If I sprinkle some salt onto this ice, then my experience says the salt will melt the ice, cause the ice to melt, and now it will be a liquid, which is much safer to drive and walk in compared to ice. Okay, so we have to again think about this. It's still minus 10. We didn't change the temperature. It's still minus 10, but now the water has melted. Can I get that water to freeze? I can, but I need to lower the temperature even lower, maybe minus 60 or minus 70 or something like that, right? Then this will refreeze. So I haven't changed the freezing point of water to a higher value, like from 0 to 10. I've taken it to a lower value, like from 0 now down to minus 30 or minus 40, necessary to freeze this salty water. Okay? So that's critical. We have to be able to remember that. You have to be able to remember that the freezing point depression is what occurs when a solute, and it doesn't need to be salt, it can be any solute, is added to a solvent. That liquid, the solvent's freezing point will be depressed by the addition of any solute, according to this formula right here. The change in the freezing point will be equal to the molality of the solute in the solution times that solvent's constant, freezing point constant. Okay? Now, let's have that was our little conversation about how adding a solute to a solvent changes the freezing point of that solvent. Okay? And we have to remember that. Let's see how well we did. All right. Who did we talk to? I think it's Sarah's turn again. Sarah, if we put salt into water, at what temperature, which of these temperatures, if I have a solution of salt and water, which of these temperatures would be a reasonable temperature for the solution to melt at? So we're looking for the melting point of a solution of salt and water. Okay? So A, 293 Kelvin, B, 273 Kelvin, C, 300 Kelvin, D, 200 Kelvin. So, Sarah, if I have, what is the melting point of a solution of sodium chloride and water? Which one of these is a reasonable melting point for a solution of sodium chloride and water? What do you think, Sarah?
So, I would think maybe D, because you said adding salt lowers. I'm not sure.
That's right. Very good. So 293 Kelvin means we're at approximately what Celsius? That's 20 degrees Celsius, right? 273 Kelvin, that's 0 degrees Celsius. 300 Kelvin, that's 27 degrees Celsius. Is that right?
Can you explain how you know that?
Oh, how do we know our Kelvin Celsius conversion?
Okay, subtract the 73, right?
Yeah, that's right.
Okay.
So here, when I subtract my 273, I'm ending up at a negative 73 degrees Celsius. And this is one that is lower than the typical freezing point of water of 0, right? So this is the only one that could be an actual freezing point. As you add salt to water, you don't raise the freezing point of your solvent, your solution, resulting solution, right? You can only lower. And this is where you would start, so you wouldn't be at the same place either. All right. Now, again, it takes some thinking, holding still, just thinking about why do they put salt on the roads, all right? There's also a notion out there, I don't know where it comes from, that you can't freeze salt water. That's not true. The water up at the Arctic poles and stuff like that, it's salty. So there's plenty of, you can get cold enough to freeze salt water. You do have to get colder than the freezing point of water, but you can freeze salt water. Okay. A little story, little conversation about boiling point. Boiling point. Boiling point elevation. Aisha, did you have a question? Or does anybody have a question for that matter? Okay. So, if we have the boiling point of a solution, I don't know if you guys have heard this one, but if you take a pot of water that you're planning to cook spaghetti in, all right? So I have some noodles. They're not cooked. They need to go into the pot of water, get softened up and cooked, okay? Now, some of you have some cooking experience or have been taught by grandma that you need to put something else in here. What else do you use? I mean, not everybody, and it's not required, but highly recommended. Does anybody know what they're supposed to be putting into this to the pasta when they cook it? Any ideas? You can type it down in the chat box below. Salt. That's right. We're supposed to put salt in there. Okay? Why? Why do we add salt, Grandma? Well, I don't know. Do you guys remember having this conversation with your grandma a long time ago? Why is it that we add salt? Anybody know?
Doesn't it lower the boiling point?
Okay, so it lowers the boiling point. What would that mean? That would mean that if I have water without salt, here's the water without the salt right now. What point will it boil at? Was that Alyssa?
I'm not sure what it is in Kelvin.
Oh.
Like 307.
Yeah, we can use degrees Celsius. That's fine. 100 degrees Celsius, right, is the temperature what it boils at. Okay, water boils at 100 degrees Celsius. As a side note, let's think about this. I have this really cool tool at home that looks like this, and it's blades. And I take a potato and I stick it on there, and then there's this other part of the tool that pushes the potato down onto the blades and makes these. What are these? Anybody can tell me in my box below? What have I made by pushing the potato through these blades?
French fries.
French fries, that's right. French fries. And after we get French fries, as everybody knows, the best way to cook French fries is to stick those French fries into a pot of boiling, well, not boiling, but, well, hopefully, maybe boiling
Simmering.
water, right? Isn't that how you make good French fries? Why don't we do that, Camille? Why don't we make our French fries in water?
Because it doesn't make them crispy.
Why doesn't it make French fries crispy when we put it into water? Because water can't get hot enough. It can't get hot enough. It can get, how hot can water get, Camille, do you know? How hot can water get on the stove? Anybody? It's right over here, right? Why can't it get higher than 100 degrees Celsius? What happens if you get hotter than 100 degrees Celsius?
It evaporates.
It evaporates. That's right. So nobody makes French fries by putting it into water because you need hotter solvent. And you can't get hotter than 100 degrees Celsius in water. As you add more temperature, more heat, more heat, more heat, it won't go to 101, 102, 103 because the water evaporates. All right? So if I put salt in this water and then the water begins to evaporate at a lower temperature, that would be like if I could get it down to 90 degrees Celsius by adding salt, that would be a problem because then my pasta wouldn't cook as well. It wouldn't cook as fast, right? Because it's not very hot. So, we don't put pasta into water and just leave it out overnight. And we heat the water to speed up the process, right? So adding salt to water doesn't lower the boiling point, but it does what, Alyssa?
It raises it.
It raises the boiling point. It raises the boiling point. Okay? Now, Grandma might have told you something else. Grandma might have told you it lowers the boiling point so it boils faster. Well, that wouldn't be very helpful, right? Because if you lower the temperature, it doesn't matter how fast the water's boiling, the lower the temperature, the slower these pasta things are going to cook. My grandma told me you add salt because it raises the temperature at which the boiling occurs. Therefore, the pasta cooks faster. All right? That's what I was told. But even that is not the real reason you add salt to pasta. Okay? The real reason you add salt to pasta is because it makes it taste better. Okay? And we'll learn that in a question later on, because we find that the amount of salt you would need to make a significant difference in the boiling point of water is far too much, right? Nobody would add that much salt to their pasta water to change the temperature just such a small amount. Okay, but those two stories, the story of the ice on the roads and the story of the salt in the pasta water, right, need to help you remember what happens when you have a solute in a solution, right, how it changes the boiling and the melting point of those solutions. Look at this here, it decreases the freezing point. So here is your ice going to liquid phase. The ice has the freezing point of the solution is red here. The freezing point of the water is blue. So it lowers the freezing point, and it here's the temperature here. If you look across a line this way, so like this one, for example, it raises the boiling point. Raises the boiling point. All right. And then you have the constants. The constants, KBP. You're going to look at KBP and say, I don't know what that means. BP sounds something like boiling point. But when you're stuck in that situation, Alyssa, what is our, is it Alyssa? I think it's Landon. Landon, what's our recourse? What do we do when we see a constant like this and it doesn't make any sense to us?
A constant like, which one? Sorry.
Well, we have this one here. It says KBP. We have this one KFP. You know, we talked about it a long time ago. It's test time. I can't remember what to do with this. What am I supposed to do? How do I? What?
I would say try to find how they relate to the other variables.
Through their what? It's their units.
Relationships.
Their units,
Yeah,
right?
units.
That's right. So the units here are the way that, you know, they try to make the problems hard, but they can't, because it says right here, KBP, whatever that means, has to do with degrees Celsius per, what is that little m there, Landon? Molality. That's right. So this is the shift in degrees Celsius per molal of solute in our, whatever our solution is here, or our solvent is here. Okay, so it's nice of them to put a plus here, but they won't always do that for the boiling point or for the freezing point. So we have to recognize the shift that will occur based on our understanding of why people think about putting salt in water and the boiling point, and why people put salt on icy roads, right? So let's see how we do. According to this antifreeze, the freezing point of a 4060 solution of Sierra antifreeze and water is 4 degrees Fahrenheit, or minus 20 degrees Celsius. So what's the molality of the solution? What's the molality of the solution? Well, 4060, what does this 4060 mean, Aisha? Oh, Camille, sorry, go ahead, Aisha, you can get this one. I see Camille's available too, though. Aisha, what's the 4060 meaning? The mole fraction, I mean, it's going to be a 40-60 mixture is going to be a mixture of the antifreeze and what? What does the 60 represent here? And water. That's right. So from this 40-60 information, and maybe it was already intuitive, but we know that the water is our solvent. And so we can go back here and look at the conditions for water. Now they're looking at the change in the freezing point, right? So we look here for water, normal freezing point 0, and then we have 1.86 degrees Celsius per molal. 1.86 degrees Celsius per molal. So I'll write that down. The K of freezing point for water is 1.86 degrees Celsius per molal. Now, the minus 20.
Wait, I have a question.
Yeah,
I thought that and with the line under it was molality.
yeah. What was I saying? Was I saying molarity?
I don't know. I
Okay.
was just confused. Sorry.
No, that's right. That's right. It's molality. And just like you could say, for example, here's a solution over here. This is the solution. It's a 1 molar, big M, solution. Its molarity is 1, or I can say it's 1 molar. All right? And if I change this now, it's 1 molal. Its molality is 1, and it's 1 molal. So depending on how you say it. So
That makes sense. Sorry.
maybe that's
I
what I
just
think. That's fine. So we have 20 degrees Celsius is our shift, right? It went from 0 down to minus 20. So 20 degrees Celsius is our shift, and that is the freezing point, 1.86 degrees Celsius per molal times the molality. All right, so just 20 divided by our 1.86 should tell us what the molality of our solution was. Okay, very good. So, pretty straightforward. One thing that we have to remember is it's not telling us the new freezing point. It's telling us the change in the freezing point, right?
I
And
have a question.
yeah, go ahead.
What do we do with the -4?
The -4, well, that was
Yeah.
in Fahrenheit, and
Oh, okay.
our constant was in Celsius, so it was just helping us Celsius-minded, or if we can't convert between Celsius and Fahrenheit very well, and we only understand kind of what Fahrenheit means, then this kind of helps us a little bit. But that's what that was for. Okay, very good. So it's a pretty straightforward relationship again, and the constant will always give us an indication as to what we need to multiply it by. It's going to be in degrees Celsius per molal, so we need to find the molality. And again, we need to remember that it's a change in temperature, not the actual boiling or actual freezing point of the compound. Okay, good. I think we're going to skip this one. And I think we're also going to skip this one. And that one as well. Maybe if we have time here at the end, we'll work on one more problem from the book. But let's look at, let's see. Yeah, I think we want to skip to this one here. In preparing pasta, 2 liters of water at 25 degrees Celsius is combined with 15 grams of salt, and the solution is brought to a boil. And we would like to know what the boiling point of the water will be. Okay, so we have 2 liters of water, and we have 15 grams of salt. 2 liters of water, 15 grams of salt. What will be the boiling point of this solution? Okay. Whose turn is it? Camille, I think it's your turn. Camille, what would we do for this problem? Where would we start?
I'm reading it.
Okay.
We need to find the boiling of water, correct? Wait, no. Okay, oh no, we're finding the water. Sorry, find the water. I need help. Sorry.
All right, well, what's the boiling point of water without the salt?
1.86.
1.8.
No,
What's the boiling point of water? Just the boiling point of water. That's what we're. Do you remember that?
is it the 1.86? Oh, 100.
100 degrees Celsius. That's right. So 100 degrees Celsius is the boiling point of water. And I think the first thing we have to get in our mind is how will this boiling point change when we add salt?
Okay. So the boiling point will it go up?
That's right. It will go up. It'll boil at a higher temperature. It'll take more energy to make it boil. Okay? I didn't finish my little story about the French fries, right? We put potatoes into oil because the oil can get very hot, right? Over 400 degrees Celsius and still not begin to boil at all. I ask students all the time, have you ever seen oil boil? Have you ever seen boiling oil? And usually students say, yes, I have. When I make French fries, I see it boil all the time. Or at work, when we fry those chicken patties or whatever it is, I can see it boil. But it's not boiling. Oil doesn't boil at the temperatures that our stove provides. What we're seeing is the moisture, the water on the food going into the oil and then evaporating away. That moisture is evaporating away very quickly, and that results in boiling of the water on the surface of the food. And that high temperature gives us the flavor that we want and the texture that we want on French fries, on fried foods, right? And that's why we don't put potatoes into water to make French fries. We can put potatoes in water and make mashed potatoes. That's not a big deal. But so yes, the boiling point of the water is going to increase. The boiling point of the water is going to increase. It's going to increase according to what parameter for the salt? Aisha, what way of expressing the concentration of the salt do we need to know to see how the boiling point of water is changed? The mole, specifically the molality, right? The molality. So we want moles of NaCl over what? Kilograms of solvent. Very good. And then once we have the molality, we can multiply it by the K boiling point of water, and that will give us the change in temperature of our water. Okay? So, let's go back to this slide up here. Where's our boiling point of water? Here it is. Water. Which value are we looking for, Aisha? That's right. The 0.51. This is the boiling point. 0.51 degrees Celsius per molal. 0.51. So, 0.51 degrees Celsius for every molal. Okay. Taiwan, how do I find the molality of salt in this question here? How do I find the molality of salt? How do I find the molality of salt, Taiwan? Moles of NaCl divided by kilograms, not liters, of the water. That's right. So if I have 15 grams of NaCl, I need to convert that to moles of NaCl. Is that 20? My chloride ion is, oh, they gave it 58.44. There it is. So 15. There's my moles, 0.257. All right. How many kilograms of solvent, Sarah?
I'm not sure we know how many liters we have.
Okay. If I have 2 liters, how many milliliters is that?
1,000.
Or 2,000, right? 2 liters?
Oh, you're right.
2,000 milliliters. Now, they didn't tell us the density of this solution. But what do you think the density is close to, Sarah? Do you remember, did you get to do the lab? Remember putting salt into the water, checking the density of those samples?
No, I don't think so.
The density of this type of a solution, because it's almost all water, right, is going to be really close to 1 gram per milliliter. So what does that mean we could put underneath here, Sarah?
So, 2,000.
That's right. 2,000. Well, actually, we want to convert it into what? Not grams, but so 2.000 kilograms of solvent. All right. So 0.257 divided by 2,000. 0.257 divided by 2,000, or not 2,000, sorry. 2.00. 0.1285 is our molality. 0.1285 is our molality. Okay? Now, we would seem like we're really close. We just have to multiply those two together and we would identify what the change in temperature is. But there's one more thing that we need to realize here. Is something happens when I put sodium chloride into water. What happens when I put sodium chloride into water, Alyssa? It dissolves, and because it's an ionic compound that's soluble, it also what?
Like separates.
That's right. What do we call that? It's dissolving and forming these two separate ions, which is called dissociation. Dissociation. So, because there's twice as many ions, or even just species, whatever they are, floating around in solution, this concentration gets multiplied by 2 because there's twice as many ions. So the resulting change is going to be my 0.1285, which is our molality, times the 0.51 times 2. All right? So why did I multiply it by 2, Landon?
Dissociation occurred with the sodium chloride.
That's right. And so I get a change of 0.131. 0.131. What is that, Landon? Is that the new boiling point of my water?
I believe that's the difference between the normal boiling point of water and the new.
All right. So the new boiling point is going to be what then, Landon?
just be 100 degrees Celsius plus 0.131.
That's right. Very good. So now our new boiling point is 100.1 degrees Celsius. Very good. So, from putting 15 grams of salt into 2 liters of water, which is actually going to be pretty salty. Not going to be comfortable to eat that much salt in just 2 liters of water. The result is a change in temperature of about 0.1 degrees Celsius. Okay, so we want to make sure we captured all the different steps there. Here it's described to us, right? Our change in temperature is the molality times the boiling point constant, but then we have to make sure we multiply by more than, the number of ions that are resulting. So it's 2 in this case, because sodium chloride is dissolving in our solution. And the result is not the new boiling point, but it's the shift in the temperature. So we have to know what the previous boiling point was. We also have to remember to add that to we're adding our new value to the change in the boiling point, because it increases the boiling point when you have solute dissolved in it. All right, one last question here. If I have a solution, 1 molal solution of, or I have 5 separate solutions of these salts. So I have 1 molal sodium chloride, 1 molal iron Fe oxide, 1 molal calcium chloride, 1 molal magnesium, let's try this one, chromium nitrate. So I have 4 different solutions. Which one of these is going to have the highest boiling point, and which one is going to have the lowest boiling point? Which is going to have the highest boiling point, and which is the lowest boiling point? And I guess I should say, or are they all the same? Or do multiples have higher or lower boiling points? Let's see. Who do we got? Aisha, any ideas? Which one of these is going to have the highest or lowest boiling point? Do you know either one of them? It's going to have the what? Highest or lowest? Highest or lowest. This one, what happens when we put a salt into water? Does it raise or lower the boiling point, Aisha? It raises the boiling point. So when I put the salt in the water, it's going to raise the boiling point. So this one is actually going to be the highest boiling point. So I have other salts here. Why is it that this one is the highest boiling point, Aisha? That's right. It has 1, 2, 3, 4, because there's 3 nitrate ions, 4 different ions for every material. And if I have equal concentration of these materials, then it's the change in the ions, the highest number of ions, that's going to increase the boiling point. All right. What about the lowest boiling point, Aisha? NaCl. Very good. NaCl only has 2 ions, right? 2 ions. So this is going to be our lowest. Now, did you consider this one at all, Aisha? All right, this was just a little review, but iron oxide is not soluble in water. So that one won't change the boiling point. That'll still be at 100 degrees. And then this would be the second highest, right? 3 ions. All right, very good. So in this class, we were able to hopefully solidify in your minds how the boiling point and freezing point of solutions shift when solutes are dissolved in them. And it's based on the molality of the solute that's dissolved in the solution. And also, if our solute that's dissolved is an ionic compound, it's not just based on the molality of the compound, but the resulting molality of the ions themselves. Very good.